This video. Namaste. In this session, we will discuss mixing of ideal gas and its relationship with chemical potential, Gibbs free energy, and entropy of the system. So, we will study the Gibbs free energy associated with mixing of ideal gas, entropy change associated with mixing of ideal gas, and chemical potential associated with mixing of ideal gas. Before going into true mixing exercise, we'll first study two elementary thermodynamic expressions. So from thermodynamics, we know that molar Gibbs energy of pure ideal gas can be expressed in terms of pressure, and the expression goes like G is equal to G0 plus nRT ln P by P0. Here P0 is standard state pressure and which is equal to 1 bar, and G0 is the standard state free energy. So again, this expression is for molar Gibbs energy, and molar Gibbs energy is nothing but same as chemical potential. So I can also express this equation 21 in terms of chemical potential. So if I do so, the expression goes like chemical potential of ith species is equal to chemical potential of ith species in standard state plus RT ln P by P0. So these are the two elementary expressions. Basically, I'll use this expression 22. Equation 22 in while we'll be discussing mixing of ideal gases. Now there is an important point here. The P0 is 1 bar. So if I replace 1 bar, this denominator goes away. But when the pressure units of pressure are either in 1 bar or expressed in bar or ATM, atmosphere, then only I can put here 1, otherwise I can't do that, because 1 bar is almost same as 1 atmosphere of pressure. So when while solving problems, this should be monitored judiciously. If the pressure unit is given in a different unit other than bar and atmosphere, then you have to consider P0 also. So with that, you go to the mixing of ideal gas. Consider two containers containing pure gas. In one container pure gas A and in the other container pure gas B. Now the figure is not so accurate, but assume that the containers are in contact with each other and there is a membrane separating them. Now if I want to remove the membrane, I can remove that so that the gases will mix with each other and uh, and and the volume will also increase. Initially, let's consider for gas A, the number of moles are Na, temperature was T, volume was V1, and pressure was P. Now after mixing, two things will change. The first thing that will change is volume will increase. There is a larger volume available for the gas now. As there is a larger volume available for the gas, consequently the pressure of the gas will decrease. So pressure, initially the gas pressure was P for component A. Now the gas pressure has reduced to PA, that is partial pressure of A. Similarly, there is partial pressure of B also, and both the partial pressure mix up to give a total pressure. And the important point to note here that pressure of individual component decreases after mixing and the total system is isolated. So we'll keep this problem in mind and go ahead with solving the ideal gas mixer problem. So as I said, we will discuss three things: mixing of ideal gas and what its effect on chemical potential, what is its effect on free energy chain, and what is its effect on entropy change. So first we will discuss mixing of ideal gas and chemical potential. While discussing chemical potential, let's consider only one component. Let that component be A. So here from this figure, gas A is in pure state. This state is the pure state, and after mixing, there is a mixing state. So we'll find out the expression for chemical potential in pure state for gas A and mixing state after a state the gas mixes. So after mixing, what is the chemical potential? So we'll find out two chemical potential: before mixing, after mixing. So before mixing, we'll call it as pure gas. So the chemical potential of pure gas A is equal to mu A0 plus RT ln P by P0, same as equation 22, expressed in terms of gas A. Now after mixing, what will happen? mu A mix is equal to mu A0 plus RTLN PA by P0. This P0 is 1 bar. Now the change that is associated is the pressure, gas pressure has decreased from P to PA, partial pressure of A. That is the only change that has taken place from pure state to mixing state. So there is a common expression which relates partial pressure and total pressure, and it goes like partial pressure is equal to mole fraction into total pressure. So I can write PA is equal to XA into P. So I'll substitute this PA in the chemical potential of mixture of gas for component A. Then I'll get, suppose I substitute PA is equal to XA into P. So I'll get two terms now, RTLN P by P0 plus RTLN XA by P0. Now the first two terms, mu A0 plus RTLN P by P0 is nothing but chemical potential of pure gas A. Chemical potential of pure gas A. So if I substitute that, what I'll get? I'll get chemical potential of pure gas A in the mixed state is equal to chemical potential of gas A in pure state plus RTLN XA. Now there is this equation 23 is important. Now there is an interesting property here. XA is the mole fraction of gas A. Similarly, there is mole fraction of gas B. Now both the mole fraction sum up to 1. So essentially XA is always less than 1. So ln XA will be always be negative. So RT ln XA will be negative. Now what is it? What it states? Chemical potential of gas A in the mixed state is equal to chemical potential of pure gas A minus some negative term. So I can say chemical potential of pure gas is greater than chemical potential of mixed gas for gas A. So this is the driving force for the mixing. Means the gas A was at a higher chemical potential before mixing, and after mixing the chemical potential of the gas A decreases, and that is the driving force which drives the gas for mixing. So I can when the mixing takes place, a stage of an equilibrium state is achieved, and at equilibrium state both the chemical potential, means pure state and the mixed state, becomes equal for any component of the system. So I can say that chemical potential is analogous to electrical potential and mechanical potential. What happens in electrical potential? Charge flow from a higher potential to lower potential. What happens in a mechanical potential? Any system at a higher mechanical potential energy tends to go towards a lower potential energy, like flow of water. Water flows downhill. No, at a greater height it has higher potential energy. At a lower height it has a lower potential energy. So similarly, chemical potential is analogous to electrical potential and mechanical potential. Any species with higher chemical potential tends to decrease its chemical potential. So that is the driving force for mixing of ideal gases. Now what is we'll try to understand the mixing of ideal gases in terms of free energy change. So as I am saying, free energy change, so we have to find out free energy in the initial state and free energy at the final state. And from equation 6 we know free energy for the initial state can be written as mu A Na mu B Nb. Now I will pull up the expression for mu A and substitute mu A0 plus RTLN P and mu B0 plus RTLN P. Again here there is a division of P0. I am assuming that the P0 is 1 bar, and this P is also expressed in terms of either bar or atmosphere. If this P is expressed in different units, then I have to mention this P0 as well. Now similarly I will write an expression for free energy change of the final state. I can write an expression similar to that of initial state. Now the change in Gibbs free energy will be equal to final state minus initial state, which will essentially give me NaRT ln PA by P plus NbRT ln Pb by P. What is Pb? The partial pressure of gas B after mixing. What is Pa? Partial pressure of gas A after mixing. What is P? This is pressure of gas A before mixing. This P is pressure of gas B before mixing. Now we'll use some of the common expressions. We know partial pressure is equal to mole fraction into total pressure. So I can substitute this Pa by P age XA, mole fraction of component gas A. Similarly, PP by P, age XB, I can substitute. Similarly, I'll multiply N. What is N? N is equal to total number of moles, and that is number of moles of gas A plus number of moles of gas B, means N is equal to Na plus Nb. So I'll multiply N and divide by N. So if I multiply here, I'll get a N term here in the numerator, and if I divide by N, I can write that N as Na plus Nb. So what I'll get, Na by Na plus Nb, I'll get XA, mole fraction of gas A. So if I do all these rearrangements, I'll get the free energy change of mixing, free energy change of ideal gas mixing, which comes out like nRT XA ln XA plus XB ln XB. Suppose there are more number of components, then those components will be added up here, so that I can sum it up and write it in a like free energy of mixing is equal to nRT sum over I goes from 1 to n or n, whatever it is, xi ln xi. Now this equation 24 is important. We'll use this equation 24 or this free energy change of ideal gas mixing to derive the free energy change of entropy. Sorry, to derive the entropy change of ideal gas mixing, we'll use, again I'm repeating, we'll use this change in free energy of ideal gas mixing to determine change in entropy of ideal gas mixing. So now again, let's look this equation 24 carefully. There is ln xi. So ln xi will always be negative because these mole fractions are always less than 1. So the ln term will always be negative. So essentially this whole term will be negative. So that says that the mixing process associates with a decrease in free energy. Again, that hints that the process is spontaneous in nature. So now we'll study the mixing of ideal gas in terms of entropy change. There is a relation which in the last class we discussed this and we have understood this relation, which relates entropy and free energy, and the relation goes like partial free energy upon temperature at constant pressure and number of moles is equal to minus entropy. So if I take finite change, I can write delta S mix is equal to partial delta G mix upon T at constant pressure and temperature. Now I know this delta G mix. Just now I have we obtained this expression. What is this expression? This is the change in free energy of mixing of ideal gases. So we'll put the value of this expression from equation 24. So then we can get change in entropy of ideal gas mixing, and that comes out to be nR sum over xi ln xi. Mind you, for free energy change it was nRT sum over xi ln xi. For entropy it is minus nR sum over xi ln xi. Now let's look at the sign of this expression equation 25. Again ln xi will be a negative term. So this total sum over will be a negative term. But there is a negative term already there, negative sign already there. So delta S mix or entropy of mixing will be positive. So what it means, again this is a thermodynamically feasible process. Means the gas mixing is associated with positive change in entropy. Previously we have discussed that gas mixing was associated with negative change of free energy, and here we are seeing that gas mixing is associated with positive change in entropy. So again the process will be spontaneous. Now let's understand this entropy change and free energy change of ideal gas mixing through this graph. Let me scale it out. So here two graphs are there. One is this free energy change plotted as a function of mole fraction of A, and entropy change plotted as a function of mole fraction of A. Now let's first understand this free energy change. So when mole fraction is 0 or 1, when mole fraction, again I am repeating, when mole fraction is 0 or 1, the entropy change is 0. the free energy change is 0. Again I am repeating, when mole fraction is 0 and 1, the free energy change is 0, means the process is non-spontaneous. When mole fraction decreases, from 1 and increases from 0, that is at 0.5, when the mole fraction of component A is 0.5 and component B is 0.5, you get maximum decrease in free energy. Means when the gas mole fraction is 0.5 and 0.5, the mixing process will take place very spontaneously, means it will be utmost spontaneous, because at that point only the free energy change is the most negative kind of thing. Now the opposite happens in case of entropy change. When the mole fraction of component A, is 0 and 1, delta S entropy change is 0. When mole fraction approaches 0.5 or mid-range value, the entropy change achieves maximum positive value. Again, we know that maximum positive value means the process is spontaneous. So at 0.5 mole fraction value, this entropy also shows that process is highly spontaneous in nature. And then this is the same explanation as I discussed now. Now we will see isothermal and isobaric enthalpy of mixing. We have discussed chemical potential and mixing of gas. We have discussed free energy change and mixing of gas. We have discussed entropy change and mixing of gas. Now we will discuss enthalpy change and mixing of ideal gases. But the enthalpy change is associated with a condition. The condition is the process should be isothermal and isobaric, means the temperature should be constant, the pressure should be constant. So there is a thermodynamic relation, delta G is equal to delta H minus T delta S. Recently we saw what is delta G mix and what is delta S mix. We can pull up those values and substitute here. If we substitute free energy change of mixing and entropy change of mixing, then we can easily find out enthalpy change in enthalpy of ideal gas mixing, and that will come out to be 0. The enthalpy of mixing of ideal gas is 0 because molecule of ideal gas, since this is the ideal gas, the molecules will not interact, so the enthalpy change will also be 0. So I'll stop here. Next class we will discuss criteria for thermodynamic equilibrium, degree of advancement of reaction, chemical equilibrium in ideal gases. Thank you.